When atomic size is more, we can easily remove. There is no need of more ionization enthalpy. The atomic size decreases from left to right along a period and electrons are added to the same shell. Whenever the electron repulsion will be less, then the energy released will be more. For everything breaking, you need some energy, that is dissociation energy, that will be represented by ED. Hello everyone, I am Harshita Bhavasar from Vidhyaashram PU College, Temple of Excellence. Today we are talking about the classification of elements and periodicity in properties, that is on session 3. So in the last class we have discussed about nomenclature of elements with atomic number above 100 and metals, non-metals and metalloids, periodic trends in properties of elements. In that we have discussed about atomic radiation and variation of atomic radius in the periodic table. Today we will discuss about ionization enthalpy of an element, successive ionization enthalpies, electronegativity, periodic trends in chemical properties. So now we will see the ionization enthalpy of an element. So what do you mean by ionization enthalpy means? It is defined as the amount of energy required to remove the outermost electron from an isolated gaseous neutral atom. It is known as ionization potential. Means, see here, a complete atom is given, represented here. This is nucleus. Here the electrons are revolving around. From this is the outermost shell. From the outermost shell, one electron should be removed. For that, some energy is needed or required to remove this electron. That time energy will be absorbed to remove this electron. That energy will call it as ionization energy or ionization potential. So, 1 electron volt of ionization potential per atom is 96.472 kilojoule per mole. Okay, ionization enthalpy is denoted as IE and measured in kilojoule per mole. Example, this will be gaseous atom. When one electron is removed from the outermost shell, it will become or it will form a cation. This is 1 electron will be removed. Okay, if we remove from another electron from this cation, it will form a divalent cation. From again, if we remove an electron from the divalent cation, it will form trivalent cation. This means there is a successive ionization enthalpy will be seen. This is an example. This is gaseous atom of sodium. 1 electron will be removed. It will form sodium cation. For this removal, we need the energy of 495 kilojoule per mole. The energy needed to remove the outermost electron from a neutral gaseous sodium atom is known as first ionization energy, which amounts to 495 kilojoule per mole for sodium. If we remove from again the 1 mole, that will be second ionization energy. If we remove from the second ionization energy an electron, it will become third ionization enthalpy or energy. We will see successive ionization enthalpy. It is the ionization enthalpy required to remove the electrons from a cation. Means already one cation will be formed from the first ionization enthalpy. From that cation, we are continuously removing one electron to form the continuous or successive ionization enthalpy. Second ionization enthalpy is the energy required to remove 1 electron from monovalent cation. It will be represented by IE, that is 2, second ionization enthalpy. The third ionization enthalpy is the energy required to remove 1 electron from divalent cation. Okay, that will be represented by IE3. The successive ionization enthalpies vary in the following order, that is IE3 is greater than IE2 is greater than IE1. Why it is trending means This is because the removal of electron from a cation requires more energy due to increased effective nuclear charge on the outermost electron. See here, if this is a nucleus, this is the shells. Okay, these are electrons. Okay, first we will remove this electron. That time the little bit effective nuclear charge will be increased because protons are attracting towards it the electrons. Okay, next time the second electron will be removed. Already effective nuclear charge has been increased. It has been pulled. From that we have to remove, means energy is more needed to remove. If we remove the third electron, already the effective nuclear charge has been increased and the nucleus has been pulled the electrons, then we need more and more energy to remove that electrons. So the third ionization enthalpy is greater than second. A second ionization enthalpy is greater than first. Okay, this is due to the increased effective nuclear charge on the outermost electron. Okay. Next we will see the variation of ionization enthalpy in the periodic table. The ionization enthalpy decreases down the group because there is an increase in the atomic size down the group. We know that down the group atomic size will be increased. That time the ionization enthalpy will be decreased. When atomic size is more, we can easily remove. There is no need of more ionization enthalpy. The shielding effect by the inner electrons increases. That time what happened? The inner electrons, whatever the present around the nucleus, it will increases the shielding effect. I have already explained about shielding effect in the previous sessions. Ionization enthalpy increases along the period. Down the group it decreases, along the period it will increases. Why? Means the atomic size decreases from left to right along a period and electron are added to the same shell. Okay. From left to right atomic size will be decreased because the electrons which are one unit will be added, it will be added to the same outermost shell. So effective nuclear charge will be increased. That time the shrinkage of the atomic size will happen. That's why here atomic size decreases along with ionization enthalpy is more here. The effective nuclear charge increases more than the shielding effect by electrons. That's what I explained now. Hence the removal of electrons requires more energy. Okay. Next, variation of ionization enthalpies within a period. See, we are seeing some of the exemptions here. It can be explained on the basis of extra stability possessed by completely filled or orbitals or half filled orbitals in an atom. We have seen that completely filled orbitals and also half filled orbitals. By basis on these two concepts, we have some exemptions in the graph. Beryllium has completely filled orbital. Beryllium, the atomic number is beryllium is 4. Beryllium, the atomic number is 4, that is 1s2 and 2s2. Both are filled, means completely filled orbitals. Hence the ionization is higher than the boron. Okay. See, it should be increased in a order, right? But here, if you see, beryllium is 899, but it has dropped down due to the boron. Boron will be having 5 atomic number, that is 1s2, 2s2 and 2p1. 2p1 is the last electronic shell, but it is not completely filled or half filled. So, it is dropped down when comparative to beryllium. Okay, nitrogen has an extra stable electronic configuration, that is half filled 2p. See here 1s2, 2s2, 2p3. This is half filled orbital. So, it is also having an extra stability configuration. Its ionic energy is comparatively higher than oxygen. Okay. Again, if we see about oxygen, it is also neither completely filled nor half filled. So, nitrogen is having half filled electronic configuration, so it is higher than the oxygen. Same thing, neon has extra stability due to completely filled 2s and 2p orbitals. See here, 1s2, 2s2, 2p6. All the orbitals have been filled, has the maximum ionization enthalpy or energy in the period. Okay, when it is completely filled or half filled, there is a need of extra energy to remove the outermost electron, and there cannot be easily removed when it is half filled or completely filled. That is what we have explained by using this graph. See here, lithium to beryllium, it has been increased. Due to boron, it has dropped down. Again, it has been increased, boron, carbon, nitrogen. Due to oxygen, again decreased and increased. This is the trend where extra stability or the completely filled or half filled, when we have seen, these things will be happened. Next, we will see the electron gain enthalpy or electron affinity. Electron gain enthalpy is defined as the amount of energy released when an electron is added to the outermost orbit of an isolated gaseous atom. See, it is a difference. It is the opposite of electron ionization energy. There we are removing the electron from the outermost shell. Here we are adding up the electron to the outermost shell. There we can expect the formation of cation. Here we can expect the formation of anion. Okay. Example, for gaseous atom of chlorine, we are adding up of one electron. It will form chlorine anion. Here, for the formation of anion, it needs minus 348.5 kilojoule per mole. See here, this is the outermost shell. We are adding up one electron. That time, energy will be released. Okay. We will see the successive electron gain enthalpies. These are the energy changes that occur when one more electron is added to the monovalent anions or divalent anions. Okay. The successive electron affinities will be positive because the anion and the electron to be added repel each other, and energy should be provided to overcome this repulsion. First ionization enthalpy will be in minus. The successive enthalpy electron affinity will be in positive because there will be a repulsion when adding up of new electron to the outermost shell. Then due to the electron repulsion, it has to overcome. Due to that, affinity will be given in positive charge. Okay. Now we will see the variation of electron gain enthalpy in the periodic table. Electron affinity decreases down the group. Atomic size, due to atomic size increases. Okay. Anyhow, electron affinity is decreasing down the group. Why means atomic size will be increased. Already it is getting increased. If we add up, it again get increased. Effective nuclear charge will get decreased. Due to the atomic size increasing, the effective nuclear charge will be getting decreased because the extra electron will be adding up. The atomic size are getting more. So, it cannot attraction towards the outermost shell of electrons. Attraction by the nucleus for an addition electron get decreases. Okay. Electron affinity increases along a period from left to right. Atomic size decreases across the period. From left to right, the atomic size will be decreased. Effective nuclear force on the additional electron will be increases. When atomic size will be decreased, obviously effective nuclear charge will be increased whatever we are adding up the electron, because it is getting to the same shell. That's why. Hence the atom has a greater tendency to receive an electron and more energy is released. Here energy will be released during the addition of an extra electron. Okay. Since atom has a greater tendency to receive an extra energy or extra electron. Okay. These are the things we can observe in the variation of electron affinity in periodic table. Here also so many things we can see. A halogen atom becomes stable ion with octet structure by gaining one electron. Means halogens will be having, to attain octet configuration, it is needed one electron. When we add up one electron, it attains a complete octet structure by using that electron. That's what they are telling. Fluorine has less electron affinity than chlorine because fluorine is small atom which results in the inter-electronic repulsion whenever an additional electron is added to the 2p orbitals. We talked about the electron repulsion. Whenever we are adding the electron to the outermost shell, their electron repulsion will be there. Before that, the overcoming, the fluorine atom is smaller due to the inter-electron repulsion. Hence, the electron affinity of fluorine is less. Okay. In a chlorine atom, the additional electron is added to 3p orbital where inter-electron repulsion is less, hence more energy is released. Whenever the electron repulsion will be less, then the energy released will be more when electron is added to chlorine atom than fluorine. Okay. When electron repulsion will be less, the electron will be added to that shell. When electron repulsion will be more, there is no chance of getting addition of the electron to the outermost shell. That's why whenever it is adding, the atomic size will be increased or the orbital size will be increased. Based on those points, they have given this example. Next example, noble gases like helium, neon, argon, krypton, xenon have octet structure. Hence, they do not have any tendency to gain one more electron. They do not have, because it's already have completed with octet structure. They doesn't have any empty orbitals. That's why there is no capacity to gain one more extra electron also. The electron affinity of noble gases are taken as 0. However, electron gain enthalpy of noble gases are positive because energy should be provided to overcome the repulsion between atoms and electrons. Already the electrons are filled with octet configuration. Okay. If you want to add up, there is no chance. Then also if you want to add up the electron affinity, that result will be given with positive due to the electron repulsion. We have seen the rule, when the electron repulsion will be there, after the repulsion, if that energy is overcoming by adding an electron, that energy will be designated by positive sign. That's why the noble gas, since it is having octet configuration, that energy will be represented by positive sign. Next, we'll see the electronegativity. Electronegativity is defined as the relative capacity of an atom present in the molecule to attract a shared pair of electrons towards itself. Okay. See here, two atoms are present. If you see HCl, the shared pair of electrons means Cl will be having 1, 2, 3, 4, 5, 6, 7. It will be having only 1, right? Either this chlorine should attract itself or the hydrogen should attract this self. We know that obviously chlorine will only pull towards itself. The pulling of the electrons towards itself, will call it as electronegativity. Here the chlorine is more electronegative than hydrogen. The shared pair of electrons pulled towards the nucleus is known as electronegativity. Okay. Factors affecting electronegativity is effective nuclear charge. Higher the effective nuclear charge, greater is electronegativity. When the nucleus have more potential to pull the electrons towards itself, then the electronegativity will be greater. Another one, atomic radius. Smaller the atomic radius, greater will be the electronegativity. When the atomic radius is small, that time it can exhibit or it can experience the electronegativity feature very nicely. The electronegativity can be measured by two scales, that is Pauling scale and Mulliken's scale. Usually electronegativity is a non-measurable quantity. Okay. They cannot be measured. That's why Pauling showed that we cannot measure, but it can be compared with one element or one atom to another atom. That's why this Pauling scale has been introduced. According to Pauling, electronegativity difference between the two atoms A and B is given by, this is electronegativity A and B. What is this means? That is dissociation energy of A and B. How they have given means, first we have to break the bond between covalent bonds, right? Later we can bond between heteroatomic molecules. We have to break between A and B means, first the energy should be break between the bond A and A. Later the bond should be broken down between B and B atoms. Later we can break the bond between A and B. For everything breaking, you need some energy, that is dissociation energy, that will be represented by ED. Overall, root of dissociation energy of AA molecule plus BB molecule divided by 2. This is how the Pauling scale will be acting. Okay. Hence, here EAB, AA and BB, the energies of AB, AA, BB are bond energy of molecules AB, AA, BB respectively. That will be in kilocalories per mole. The unit of the scale is kilocalories per mole. Okay. Next we will see the Mulliken scale. According to Mulliken, the electronegativity of an atom could be regarded as the average of ionization energy and the electron affinity of an atom. We have seen already ionization energy and electron affinity. What is ionization energy? The removal of the electron from the outermost shell. Their energy will be absorbed. In electron affinity, adding up of electron to the outermost shell where energy will be released. Both the content or both the concepts here we have to consider and taken into average. See here, ionization energy plus electron affinity will be divided by 2. Mulliken used ionization energy and ionization electron affinity values measured in electron volts. Okay. And the values were about 2.8 times larger than Pauling values. It will be larger of 2.8 times than Pauling's scale. Okay. When we have to find out the electronegativity, you should know the electron affinity. Without electron affinity value, you cannot be find out the electronegativity in Mulliken scale. That is the limitation of the Mulliken scale. Okay. Next we will see the variation of the electronegativity in the periodic table. Decreases down the group. The electronegativity will be decreases down the group. Why? Same reasons, atomic size will be increases, the effective nuclear charge will be decreased. When the effective nuclear charge will be decreased, automatically electronegativity will be decreased. Hence the capacity of attracting electron pair will be decreased. When electronegativity increases across the period, what are the reasons? Automatically atomic size will be decreased, effective nuclear charge will be increases, the force of attraction between the electrons and nucleus will be increased. That time the electrons will be pulled towards the nucleus to enhance the electronegativity value. Next we will see the valency. Valency is the combining capacity of an element. Okay. Valency of an element depends on the number of electrons present in the outer shell or the valence electrons. Whatever the electrons present in the outer shell, that will known as valence electrons, or the octet structure minus that electrons will be represented by valence electrons. Okay. Valency of representative, that is S and P block elements, is equal to the number of valence electrons, or it is equal to the 8 minus number of valence electrons. See, S and P block, how it will be? First group will be having one valency. Second group will be having 2 valency, right? That's what they are telling. Its valence electrons is equal to the valency itself, or 8 minus valence electrons will get the number of valency. In the halogens, what will happen? It is minus 1, the valency. How? Because it is tending to get only 1 electron to reach an octet configuration. That is 8 minus 7 means minus 1 only. Like that, you have to see the valency. Whether you should see the valence electron or presence of outermost electrons present in outermost shell. Transition and inner transition, that is D and F block elements exhibit variable valency. However, common valencies are 2 and 3. It is having variable oxidation state in between. In among them, 2 and 3 are common. Valency of elements across a period with respect to hydrogen and oxygen increases 1 to 4 and then decreases to 0. From hydrogen to oxygen, it will increases 1 to 4. Hydrogen 1, again it will start for 2, 3, 4. And it decreases to 0 because noble gases having the valency is 0 only. All the elements within a group exhibit the same valency. If we see the group, first group means all the first group elements will be having the 1 valency only. If we see the noble gases, that in 18th group, all the elements from the 18th group having the same valency, that is 0. Like that, valency of the group will be same for each and every element, as the number of elements is same. Okay. Elements of 18th group have 0 valency since they are chemically inert. Inert means they are stable. Group 1, number of valence electrons is 1, valency is also 1. Group 2, number of valence electrons is 2, valency is also 2. Group 13, number of valence electrons is 3, valency is 3. Group 14, valence electrons 4, valency 4. Group 15, valence electrons 5, valency 3 or 5. 16, valence electrons is 6, valency is 2 or 6. 17, electrons is 7, valency is 1 or 7. I told you about halogens, right? 1 will be there or 7 will be there. Again 18, that is noble gases, valence electrons will be 8. Outer shell electrons I am telling, it may be valency will be 0 or 8. Like this, it may vary. We cannot tell that this is only the correct. We have to see based on its reaching the octet configuration. Next, we will see the oxidation state. The oxidation state is the number of electrons gained or lost to convert one atom into its ion. Oxidation state is related to valency itself. Whatever we are seeing this, the neutral atom is converting into ion, whether it is a cation or anion. Okay. Example, alkali metals have +1 oxidation state because their atoms lose 1 electron to form monovalent cations. Example, see here, sodium, it is losing 1 electron to form cation. Oxidation state will be +1 because 1 electron will be removed. Fluorine always gains 1 electron to form fluorine ion. It is getting 1 electron, it will form anion. Oxidation state will be -1. Like this, the neutral atom will be converted to any kind of ion to form ion and to get the oxidation state. Next, we will see the diagonal relationship. In addition to horizontal and vertical trends, there is a diagonal relationship between elements such as lithium and magnesium, beryllium and aluminium, boron and silicon that have an adjacent upper left and or lower right relative location in the periodic table. See here, lithium, magnesium, beryllium, aluminium, boron, silicon. In the second and third period I am telling. Okay, these pair of elements have similar size, electronegativity resulting in similar properties. See, these are not belongs to same period. Okay, not same group also, but diagonally having same size, same electronegativity, same similar properties also. Okay, diagonal relationship occur because of the directions in the trends of various properties as you move across or down the periodic table. For example, ionic size decreases as we move from left to right across a period, that we know, while it increases as we move down a group. This results in the ions of the same size for diagonal opposite elements. We know that ionic size decreases from left to right. Again, if we go down the group, it will increase. But what will happen by this decreasing and increasing? The ions of the same size of the diagonal opposite will get. If we keep on decreasing, this and this will become same. And similar properties will be seen, and electronegativity will be same. That's what they are telling. Lithium, magnesium are having similar properties. Beryllium and aluminium are having similar properties. Similarly, boron and silicon are having similar properties. This is about the diagonal relationship we can see in the period, that is second and third period. Next, we'll see the anomalous properties of second period elements. This is about diagonal relationship only. The first element of each group 1, that is lithium, group 2 beryllium, and group 13 to 17 boron to fluorine differ many respects from the other elements of their respective group. For example, lithium and beryllium form predominantly covalent, whereas elements of S block forms predominantly ionic. These things I have told in very first session, that is exception in S block, that all S block elements will form ionic compounds, but lithium and beryllium will form only covalent compounds. That is the anomalous behavior of second period elements. The first element of each group resembles the second element of subsequent group. This band of resemblance is referred to as diagonal relationship compounds. That's what we have seen in the previous slide about the diagonal relationship. The first element will be resembled for the second group, second element. Correct. The reason for anomalous behavior is due to the small size and large charge, to the radius ratio and high electronegativity of the first element in each group. Whenever the first element in each group having electronegativity high, it will decreases down the group. Automatically, the second group, second element will be resembled to the first element. So, diagonal relationship will be formed due to these reasons. Furthermore, the first element has 4 valence orbitals available for bonding, whereas second member has 9 valence orbitals. Another anomalous property is first element will be having 4 valence orbitals, but second member will be having 9 valence orbitals. See here, 4, 1, 2, here overall 9 will be seen. Therefore, the maximum covalency of the first member of each group is 4, whereas the other members of the groups can expand their valence shells to accommodate more than 4 pairs of valence electrons. First 2 will be having 4 only, that groups, but more than that groups will be expand their orbitals to gain the more electrons and to attain the configuration. Okay, this is about the anomalous properties and of the second period elements. Next, some of the periodic trends and chemical reactivity. Reducing and oxidizing nature. And according to electronic concept, oxidizing nature refers to the electron accepting tendency and reducing nature refers to the electron releasing tendency of atoms. According to electronic concept, reducing or oxidizing nature means, reducing means electron releasing, oxidizing means electron accepting. These are the nature of reducing and oxidizing properties. This implies that metals are strong reducing agents, means the reducing agents will remove the electrons, and non-metals are strong oxidizing agents. Okay. Nature of the oxides. Metals form basic or amphoteric oxides. Amphoteric means that will be having the characteristics of acids and bases. That will be formed by metals. But non-metals form acidic or neutral oxides. Okay, neither acid or base, will call it as neutral. Basic oxides dissolve in water to form hydroxides, while acid oxides dissolve in water to form acids. Okay, these are some reactivities of the periodic table. See here, sodium oxide, when dissolved in water, it will form base. When carbon dioxide dissolved in water, it will form acid. Okay, these are some of the chemical reactivities and reducing and oxidizing nature of the elements. I hope you have understood everything what I have done with this chapter. Thank you everyone.